Hello everyone, I am Salim Chamagat from IBM Research. I'm delighted to talk about our work on addressing target shift in zero-shot learning. This work was done with Soma from IIT Kharagpur, Samar Suranjana and Karthik from IBM Research. What is zero-shot learning? Zero-shot learning is a classification protocol where the test set has a very different set of classes from what was seen in the training. Like the ones given here, if zebra, cheetah, antelope and giraffe are in the training set, there is an entirely new set of classes appear in the test set like snow leopard and polar bear. In this setting, we are provided with an extra information how the classes in the training and test are related. This is given in terms of attribute class mapping. In the case of animals here, say the presence of black or white color on them are considered as an attribute. Or these attributes are given for the training set classes. We represent them as phi. They are also given for the test classes. Keep in mind that only the attribute class mapping for the test class is given and not any images. In ZSL training, images, labels, and phi metrics of the training classes are passed onto the ZSL algorithm, which gives us a prediction model. And this model, with the help of phi of the test set, will be able to predict on the test images. We ask a question on how one can tailor a ZSL model if the set of test classes are already known before the training process. For example, let wolf, snow leopard, and polar bear be the classes which we are interested in. We already have attribute class mapping of these classes. We can use them in ZSL learning algorithm to get a model tailored to these classes. Before we go and explain how we do that, let us go and see one simple ZSL algorithm and what target shift in zero-shot learning means. We take a simple ZSL algorithm called embarrassingly simple ZSL, published in ICML 2015. Here the prediction model is of the form y is equal to W transpose X. Here X is the image features, either trainable or fixed. One can think of them as say ResNet features. The W matrix maps features of X into the classes. In ESZSL, the W matrix is not directly learned. Rather, the matrix V, which maps images to attributes, is learned, and one can achieve W by multiplying V matrix with a constant matrix of phi, which is class attribute map for the training set. For the test set, we have W prime, which maps image features to the classes in the test set. Here, the same W prime is equal to the same V multiplied with phi prime, the attribute class map of the test classes. The matrix V learned in the training is used in the test classes. Now, let's look at target shift in attribute prediction. Let us take two attributes, say brown and furry. Say they are highly correlated in the training set. That means most of the brown animals are furry and furry animals are brown in the training set. Furry is probably a complex concept, and furry classifier might take signals from the brown color of the image to make predictions if trained on such data. If fox appears in the test class, this correlation is a good thing to have. But if test has polar bear, then this correlation affects the model performance badly. In this work, we focus on such cases where the correlation between the attributes in training and tests are different, and we try to mitigate its bad effects on the model. We will use adversarial learning to decorrelate the attributes, which has this shift in correlation. In adversarial learning setup, a representation shown in the red is learned by minimizing the loss on the primary task. So here the primary task is predicting furry here, and maximizing the loss on auxiliary task, say here predicting brown. The way it's done is we use something called as gradient reversal technique. For this model, we have a hyperparameter to balance the weights on the gradients from primary task and auxiliary task. We call it ADV weight, and let's pick say called lambda, which gets multiplied with gradients from the adversarial branch. So higher lambda, higher adversarial weight. How do we identify the best weights is a question we ask. Also, how to deal with more number of attributes, because here there are only two. For example, the AWA dataset, which is a popular zero-shot learning dataset, has 85 attributes, and the CUP dataset has 312 attributes. We will start with the weights first. We employ synthetic dataset experiment to understand the relationship between the adversarial weight and the difference in correlation among the labels. We create a two-label dataset with input instance a 10-dimensional vector X. We have primary label YP and an auxiliary label YA. We sample them from a joint distribution through which we can control the correlation between the primary and auxiliary labels in the dataset. First 5 dimension depends on the primary label as shown in the green and the next 5 in the auxiliary label. First 5 dimension of the instance is sampled from 2 Gaussian distributions of the same variance and different mean, the same for the auxiliary label. The primary label decides which Gaussian to sample from. The exact same thing happens with auxiliary. In training, we fix 0.6 as the correlation coefficient between the primary and auxiliary labels, and for the test, we vary the correlation shift from -1 to 1. We train the model to predict the primary label on train set and measure accuracies on all the test set. And this plot here shows the result. The x-axis of the plot shows the correlation coefficient of the test set, and the y-axis the accuracy. So this dotted line shows the correlation coefficient in the training set. The model being compared here are baseline, which doesn't use auxiliary label, sharing, which means model is trained to predict both primary and auxiliary label. It's like multitask learning, that is no gradient reversal. And then this ADV 0.5 means adversarial learning with adversarial weight of 0.5, and ADV 1.0, 2.0, 3.0 means those weights for adversarial learning. And the gold standard, which is skyline here, is when the model is trained on the test set and tested on test set. That is the highest accuracy we can achieve. Observations from the plot. Take the case of blue baseline. The accuracy drops monotonically as the correlation coefficient moves away from the training coefficient, say 0.6. We can observe that the higher adversarial weight is better when there is a larger correlation shift. For example, adversarial 3.0 in the pink performs better than all others when the correlation coefficient of the test is smaller than 0.5, or like to the left of the negative 0.5. We also observe that when correlation increases the same polarity, that is to the right of 0.6, it is better not to use adversarial technique, and sharing often helps. Now, to the grouped adversarial learning, or GAL. The observation made in the synthetic experiments, we define adversarial weight between two labels as given in this equation. Rho as phi1, phi2 here is the correlation between the label 1 and 2 in seen classes or the train set, and rho u means it is the correlation between them in the test class or unseen class. Adversarial weight depends on the difference between these two correlation coefficients, and max and sign terms here are there to make sure that when correlation increases in the same polarity, we should not use adversarial technique. The next issue to address is about dealing with many attributes. AW has 85 as we mentioned earlier. So shall we keep every attribute as an adversarial to every other attribute? We will have 85 times 84 attributes, or 85 times 84 adversarial branches if we do that. To reduce number of branches, we group the attributes whose correlation is similar in train and test set. We do by using co-clustering of attributes using delta core, which is defined above as the distance measure. Now, about applying GAL to zero-shot learning. We have a ResNet backbone where the image first goes in and we get a common representation here, H. The model branches into group-wise representation. So these are the groups of attributes we decided earlier on by using the clustering. For ease of representation, we are just showing 3 groups here. In practice, we use much more. Every group has a primary task of predicting the label. So that's on the left. And the right one, which is basically adversarial task of adversarial label or adversarial attribute with all the labels other than the one available in that particular group. Please note that we'll be using delta core weight explain the last slide for each of the adversarial branch. The primary attribute predictions are concatenated to get the full attribute list, and then a method similar to ESZSL is deployed after that by multiplying the attribute class mapping to the predicted for predicting the classes. A ZSL loss, which can be any classification loss, is computed for in the instance, and the gradients are backpropagated. For the experiment results, this table gives performance of our model compared to other existing techniques on 4 datasets: APY, AWA2, CUB, and SUN. The last block of the table shows our model. We apply grouped adversarial learning by putting GAL here on 4 methods, which is ALE, device, and SG, and softmax. And one thing to note is that these are our implementations of the 4 methods, and GAL applied on them. So here ALE paper, which is on the top, reports much higher number than what we got in our implementation, but yet we can see that GAL actually helps. The green arrow numbers shown in this table shows how much improvement we are getting in GAL on the baseline. We also created a new split on APY and AWA dataset. We call it APYCS and AWACS by arranging classes in train and test split to increase the correlation shift. We see that overall accuracy for AWACS correlation shift split is lower than the usual split. So 52 goes to 25.3. But the GAL again helps to improve the number much more than on the normal split. We can see even the improvement as high as 70.2%. So this shows GAL is actually useful in zero-shot learning problems. You can find our paper and code here in these links. If you have any questions, please ask. Thank you.